So, so any burning questions on question 1, conversion? Right, it's a process and maybe there's mistakes along the way, but everybody okay on the process? Okay. And after I grade these, if I see like things that popped up again and again, I'll talk about those also. Questions on the circuit?
That is simplified to XOR, XOR, A, XOR, B, XOR, C.
I don't think it's an XOR.
Because it's either A or B or C.
Right, but it's not A and B, right? It's just A or just B or just C. So if you call your inputs A, B, C, call our output X. So when is exactly one of the inputs open, meaning logic 1? So it's right here, and right here. And all the others are going to be 0. And then if you K-map that, yeah, the K-map doesn't do much for you.
Good practice.
Good practice, though. So 0, 0, 1, so that term is a 1. 0, 1, 0 is right here, and then 1, 0, 0 is right here. And there's no way to combine those, right? So your cover is just going to be the 3 individual squares. So if you write that, X is going to be just the 3 min terms. So A bar, B bar, C, or A bar, B, C bar, or A, B bar, C bar. So that's unsimplified, but that's also as simple as you can make it. Mm-hmm.
So in order for you to do like XORs, it has to be a full checkered pattern?
Well, you could, in the name of trying to simplify it, observe that this looks like B XORed with C. And you could probably find an expression involving XORs like that. But unless this one is present here, it's not a straight XOR of A, B, and C. But it does look like if A is 0, this is B XOR C. So I think you could do something like if A bar is true, do B XOR C, or if A is true and B is false and C is true. Sorry, A is true, B is false, C is false. Right, and what we've done is we factored out an A bar from here and we got B bar C or B C bar, that's B XOR C. But for simplification, we're talking about using a K-map, so this is fine as your simplified version. Same thing, you could also factor out an A bar, right? Or you could factor out a C bar from these terms. And you can rewrite it in simpler ways, but I was looking for K-map, so that's fine like that. And then sketching a circuit, any issues there? Mm-hmm.
Does it say use a K-map, or are we supposed to assume that you want us to do it?
So when you're asked to simplify either a K-map or algebraically, but we're really talking about combining terms the way that a K-map does. So
we can just look at this equation and say, okay, well, K-map's not going to do us any good. You still want the K-map?
you don't have to, as long as you got confidence in that.
I kind of just scribbled over mine when it didn't give me anything.
Okay. But yeah, if you thought your K-map looked like this, but it should really have a 1 over here, which would simplify, and I see your K-map like this, right, you'll lose a point because you put that in the wrong column. And if I don't see the K-map, you'll lose, a bunch of points because you didn't simplify. So, within reason, more demonstration of what you're doing is useful, but don't go crazy.
So what if I did the K-map but then erased it because I thought it wouldn't work?
Well, in this case, you're okay because it doesn't work. But sometimes that happens, right? Sometimes I see no work and I see the wrong answer, but I can see a very faint, palimpsest type etching of what was there, and I'll usually circle it and say, don't erase your work. And if there's enough for me to see, usually I'll cut some slack. All right, these you've done a bunch of times, so unless someone has specific questions with these, I'll grade them up. And like I say, if there's some recurring theme I see in people's answers, we can talk about it next week. True, false, any questions? Want to just run through these? So a 4-to-1 mux can be built from 3 2-to-1 muxes. True? We'll go with true. We did that on the board. Any logic circuit can be built from a combination of XOR gates. No. Which is a bummer, because XORs are kind of easy to build, and they're not universal though. One can build a 1-bit memory using only NOR gates, right? You don't need to know anything about how you build memories, you just need to know that we've said NOR gates are universal. A PROM is a PLD with a programmable AND plane. That is false. So the AND plane is over here, the OR plane is over here, well, this picture here, right? So in a PROM, this is fixed. You've got all the possible combinations, and you just control the OR plane. In a PLA, it's the opposite, and in a PAL, both of these are mutable. So that's false. An unsimplified POS sometimes has fewer terms than the corresponding unsimplified SOP. Absolutely. One can connect 2 full adders to make a 2-bit adder. That is true. We don't usually do that. We usually use a half adder, full adder. But if you got 2 full adders, just feed that first carry a 0, and it's acting like a half adder. You can connect 2 half adders to make a 2-bit adder. That's false unless you add some extra stuff to make up for what you're missing in that second half adder. Don't care should be ignored when making a K-map to simplify an equation. That's false. You don't want to ignore them. They will really help you. Demux selects one of several outputs to copy an input to. That's true. That's what a demux is. 2's complement is the only way to represent negative numbers in binary. That's false. What's another way? Yeah, you could use 1's complement. There is such a thing, you just don't add the extra 1. Or you can use signed magnitude, where you have an extra bit that says is this positive or negative. Or you can use magic unicorn dust. There's a lot of different ways to do it. All right, so what the heck is this circuit? So here's X. This is X bar. Here's Y and X bar going in, so this is X bar ANDed with Y. Here's Y ORed with X bar ANDed with Y, so this is Y OR X bar Y. And this is X ANDed with this, so F is X ANDed with Y OR X bar Y. And there's a number of ways to simplify this. So some people noted that Y or X bar Y is the same as Y, right? And there's a theorem about that. But basically, if Y is false, this term's going to be false, this term's going to be false. If Y is true, this term's going to be true, and so the OR is going to be true. So you could replace this with Y, and you just get X ANDed with Y. Or you can spell the whole thing out and then go to town with your algebra. So this is XY or X bar Y. And there's a theorem X ANDed with not X is always false. So this is 0Y, which is just 0. And so this is just XY. And so a simpler version of this circuit is just this. Close is good. Write a truth table for a 1-bit full adder. How many times have you done this so far? It should be at least a few, right? So the inputs are A, B, and C, N. And the outputs are sum and C out. And you just do the pieces, but you might have even had this on your note sheet. So sum is going to be 0, 1, 1, 0, 1, 0, 0, 1. And carry out happens when you have at least 2 inputs that are a 1. So no carry in those first 3 cases, but here the 1, 1 will give you a carry. This 5th row is okay, but then the remaining rows you have at least 2 1s, so you're going to get a carry out from there. And the non-simplified SOP, that's just an exercise in filling in the midterms. So A bar or B or C in, A bar B C in, or A B bar C in, etc., etc. Well, I guess we'll do those to fill in this part. So, so what's C out equal to?
A naught, B naught, C.
A naught B C.
Oh, I know that.
Yeah. Or
Not B, C.
say again?
A, B not, C.
Okay. Or A B.
And then A, B, C.
We could have done it in the other order, but it's nice if it's in the same order as the rows top to bottom. All right, and then what about sum? Mhm. Look familiar? All right, so different ways you can put this on a fuse map, but let's kind of do it in the same order we've got here. So I'll call my inputs A, B, and C in, so we're not even going to use this input. And this might be C out. And we'll put sum over here just to be different. So C out, we want A bar, B, C in. So that's going to get ORed. We also want A, B bar, C in. That'll get ORed. And we want A, B, C in bar. And we want A, B, C in. So that'll generate C out. And then for sum, A bar, B bar, C in. So I'm just going to start down here. A bar, B bar, C in. So that'll go into the sum. A bar, B, C in bar. Why do I feel like I did something wrong already?
No C bar.
Yes. C bar. A, and you can always like wipe out the whole line and just start a new one. And then A, B bar, C in bar. And then A, B, C in, we've got that up here, so we could tap into that right here if we wanted, or we could make another row, since we've already got hardware. So you can do that, or you could just put an X right here. And there's a fuse map for a 1-bit full adder.
Could you go over how you get the sum and C out on the first part?
You mean these?
The A. I don't understand how you get.
Oh. So, pencil and paper edition. I should figure this out sometime because it should be really handy. Alright, we have an implicit carry of 0 in this first column. 0 plus 0 plus 0, we're going to write a 0 here, and the carry is 0. So 0 plus 0 plus 0, right, which is this first row, generates a sum bit of 0 and a carry out of 0. So that's how we fill in that first row.
Where are you getting those two zeros though from?
These?
That's what I'm confused by.
Mm,
Like, what are you using A, B, and C to get?
we're adding 3 bits together. So we're doing 0 plus 0 plus 0.
And that would be A, B, and C in?
And it's going to be equal to sum, and some carry out.
Okay.
So 0 plus 0 plus 0 is 0. So it's a sum of 0 and a carry out of 0. 1 plus 0 plus 0 is 0, 1. So it's a sum of 1 and a carry out of 0.
Okay. I was in my issue now.
But if you do something like 1 plus 0 plus 1, that's 2, right? So your sum is 0 and your carry out is 1. So 1, 0, 1, your carry out's 1, your sum is 0.
Okay.
How do we get the carry in of 1 in the second part, other than just counting in binary and allow?
What do you, oh, here?
Yeah.
You're just counting in binary. So
Okay.
when you make a truth table, you need to list every possible combination of all your inputs.
Gotcha.
And the easiest way, probably, once you know how to do it, is to just write out all the numbers in binary in order. But sometimes people just try to think out what the different combinations are and hope that you end up with 8 and that they're all different. But if you know how to count in binary, you can do that. But the other option is to do this trick. So start on the right, and there's 2 possible values for Cn, either 0 or 1. Okay, if you want to add a b, replicate your table so far, and in the top half, set b to 0, and the bottom half, set it to 1. Now you want to add a third variable, replicate your table so far, and in the top half, set your new variable to 0, and the bottom half, set your new variable to 1. And there's all your combinations, and they're in the right order.
Gotcha.
So if I had a fourth variable over here, I'd write these same 8 rows down here. The top half I'd write a 0, the bottom half I'd write a 1.
Good to know.
Yeah, it's a handy trick. This is going to be my answer key. There we go. I'm half done with my midterm now. I'm not quite half. All right, any other questions on that? Yes?
For octal, is it 250?
Oh, I don't know. Let's find out. So 168 divided by 2 equals 84 with a remainder of 0. 84 divided by 2 is 42 with a remainder of 0. And then 21. And then a remainder of 1. And then 5 with a remainder of 0. Remainder of 1. Remainder of 0. Remainder of 1. And then we're going to get 0 with a remainder of 0 forever after.
Do you care what way we do it as long as we
No,
show
if you trial and error it or something like that, that's fine.
Okay.
As long as you've got the answer. So this is your least significant bit over here. So 0, 0, 0, 1, 0, 1, 0, 1. And then sanity check. So this is 8, this is 32, this is 128, 128 plus 40, 168. So you can always check your answers on these kinds of questions and make sure you got the right answer. So that's in binary. So hex, we split it in half. So what's this look like in hex? A8. So 1, 0, 1, 0, that's the number 10. We don't write 10 because it's not a single digit. So we write an A. This is 8. So that's A8 hex. So octal, split into groups of 3. 3, 3, and there's an extra 0 in the front. We'll just pretend it's there, so that's a 2 and a 5 and a 0 octal. Very good. And you could sanity check these if you wanted to also, but usually if you do this correctly, right, you can be pretty confident of it. But if we converted this to decimal, this is the 8th place, so it's 5 times 8, and this is the 64th place, so 2 times 64. Here's your 128 plus 40, that's 168. So that looks good. And this is 8 plus 10 times 16, that's 160 plus 8, there's your 168. All right, let me hand back homeworks that came in on Tuesday. Joseph. Abraham. Tati. Kyle. And Roman. All right, any questions on the labs? Either follow up on lab, whatever the lab was with the adders, or the new lab with the sequence of blinking lights. Good on labs. Okay. Yeah.
Do you have any idea why it would be shifting to 4 different numbers instead of 8? Once I got my clock.
Does it do 4 numbers and then go back to the first, or does it do
Yeah.
4 and then wait for a while?
No, it does 4. I have 3 lights just to test it, and one of them never turns off.
Oh, okay, which is why it's doing 4. So why would one never turn off? It could be a wiring issue.
It's definitely a wiring issue. I just need to go think about it.
Yeah, you've got your 555. You've got pin 3 going into your 7493. You've got your outputs from here going into your 74-138. And you're looking at these outputs from your counter, and one of them's always stuck, right?
Yeah.
So I don't think there's an easy failure mode for that. So my suggestion would be go directly to the pin on the chip, right? And put a multimeter there and watch the voltage.
Okay.
Right, it's changing every second or two, so it'll be slow enough for you to see, and see if that voltage ever goes high, or if it ever goes low, because it's permanently on. And if it doesn't, then there's something weird, but if it does, then you've just got a connection that should be going to that pin and isn't.
What are you looking for on the part where we sketch what we think the light looks like for 555?
Oh,
And then compare? 'Cause, I mean,
so there's
pretty
a
much
pair of
synonymous.
equations. Right, there's a pair of equations for time high and time low, based on the resistors and the capacitor. So plug those numbers in, figure out how long this should be high and low in seconds, and then draw a sketch of it. Right, maybe a piece of graph paper, so high and low, and high and low, and how big is this, and how big is this, and you expect that to be 5 volts. And then look at the output on an oscilloscope, and see if you can figure out what the actual waveform looks like. And it's not gonna look exactly like yours, but it should be pretty close to your approximation. and then think about why might it be different from the theoretical.
Okay.
I had a similar issue where one of the counter, after the counters outputs was stuck on, and my resolution for it was adding a resistor in to the output from pin 3 of the
555?
of the 555. For some reason that allowed it to work properly.
You mean the resistor going to pin 8?
Yeah, from pin 3.
Just in series with pin 3?
Mm-hmm.
That's a little disturbing. It's cool that you discovered that though.
Maybe
Well,
you build a new 556
Yeah,
timer.
there's a 556. Yours can be the 557. What made you think of putting a resistor in? Just curious.
I double checked the output coming from the 555 using an LED as well as a resistor running together.
Mm-hmm.
And while that was in
Oh, okay.
the counter would take properly.
Okay.
So I took the LED out, ran the resistor from 3 to ground, and it worked just fine.
Oh, from 3 to ground.
Yeah.
Okay. That's interesting. Okay. I'd be interested in seeing your circuit if you still have it built, because there might be something else going on. But that's a cool fix. So 74 LS93, are you using input B?
Yeah.
Okay.
B, C, and D.
So if you were accidentally using A, right, then you'd have 2 lights that were stuck. So that's not going on. If you didn't have these set up correctly, then all of your lights would be stuck. So yeah, check pins 9, 8, and 11. And make sure you've got wires plugged in there going to the LED.
Okay.
And if you do, then something weird is going on. But I can also look at that with you right after class if you have a few minutes.
Okay.
Okay, cool.
9, 8, and 7?
Looks like 9, 8, and 11.
Oh, and 11.
Yeah. Other questions, comments? All right, so we've got 11 minutes left and we just had a midterm and the room's hot. And I'd like to start getting further into memories. So let me talk about this in generalities for a few minutes and maybe a few specifics, but we'll definitely drill into this a lot more on Tuesday. But let me give you something to think about. So the adder experiment, for example, right? We saw the truth table for the full 2-bit adder, right? Before we talk about half adder, full adder, we made a truth table for 4 incoming bits and 3 sum bits coming out. And we said there's 16 rows and there's 3 outputs, right? And then in the lab, you were supposed to write an equation based on that truth table for each of the outputs. Look at how many terms there are, the literal count, and then switch gears and do this half adder, full adder design. And the idea of the half adder, full adder is we have this block. It's bigger than just an AND gate or an inverter. It has more complex functionality. It takes in 2 bits, it generates a sum, and it generates a carry out. And then we have a second block, which is a full adder, which is the same thing, but it also has a carry in. And in the lab, you needed to design these. You needed to write the truth tables and write equations and simplify them and draw a circuit diagram. But once you have this available to you, right? Imagine you're trying to build a 2-bit adder. Well, you go into your parts box and you open it up, and there's a chip, and it's labeled half adder. And it's one of these things. And you have another chip, and it's labeled full adder, and it's one of these things. Very easy to build your adder now. Take your full adder, connect 2 switches here. Take your half adder, connect 2 switches, tie that to that. Put these 3 into your LEDs or your 7447, and you're done, right? Most of the wires and chips on your board were actually building this thing and this thing. Okay, but in practice, we're usually not building things gate by gate, chip by chip, right? We're usually starting with something more powerful, like a half adder or a full adder. Or, for example, in the current lab, you're building a light sequencer. Now, I erased it. Your counter, your 7493, is a fairly complex device. It's got all of this stuff inside here. And each of these is a set of 4 NAND gates, cross-coupled, plus some other logic. So this is a really big, complex unit. But we don't deal with it at that level. We deal with it at the level of, hey, guess what? I've got a 7493. It's a counter. This is the input, it's the clock. When the clock changes, the outputs change in some way. Same thing with the decoder. We could write a truth table, 3 to 8, big long truth table, 8 rows, 8 outputs, write the equations, minimize, and so on. But we don't do that. We have this in our parts box. We have this in our parts box. And this is a mindset we're shifting into very quickly now at this part of the course. We're going to start developing circuits based on circuits we've already developed. Okay, so on Tuesday, we talked about a pair of NOR gates connected to each other, right? So it's like 2 inverters feeding each other, but we use NOR gates. And we started looking at the behavior of that, and I said it's something called an SR latch. So I'm going to remind you what an SR latch is in a minute. But starting Tuesday, what we're going to do is we're going to take that SR latch and we're going to assume that this is a single unit. And we're not really going to think about it as here's a NOR gate, and if you put a 1 in here and a 0, you get a 0 coming out, and you get, right? We're going to think of it as an SR latch, and we're going to try to understand what that means. The reason being, we're going to take that SR latch, we're going to add some other circuitry outside it, and we're going to create something called a D latch. And once we understand what a D latch is, we're going to take a pair of D latches, add some more circuitry, and create something called a D flip-flop. And if we have a D flip-flop, we're going to take some of those and put them together into other things and create a T flip-flop and a JK flip-flop. And at any point, we could go back and we could draw this in terms of a billion, maybe not quite a billion, but a billion of these things, these cross-coupled NOR gates, right? But if we have to go back to that level every time, it's going to make life really confusing. So as we start developing new functional blocks, starting with an SR latch, we want to try to get comfortable thinking about the functional behavior of this unit so that we can use it in other things, just like we don't talk about this as a truth table or a series of equations. We think of it as this 3-bit input selects one output to drive low. And we just think of it, it's just a box that does that somehow. Okay? This is exactly what we do in computer science. It's a concept called encapsulation. We use pieces of code that are provided to us, and we don't need to understand how that code works. We need to understand what the code does, but not how it does it. So here's a piece of code. If I call it with these arguments, this is the result. But very deliberately, the details of how that result comes about are usually hidden from the person who's using it. Okay, so there's this concept of information hiding along with encapsulation, just thinking of the function. So we're going to do that going forward next week. And once we've done this and we've built ourselves up to JK flip-flops and T flip-flops, then we're going to start designing state machines. Okay, these are small computers. And we're going to use the mechanisms that are available to us in these flip-flops with some extra circuitry added on to create machines that will predict the weather or do other crazy things. All right, does that make sense? So let me give you a quick rehash on SR latches. And we'll call it a week. think I got those right. So this was what we were developing. We're gonna hide all of this stuff. We're gonna think of this from a system diagram point of view. So this is our SR latch. It has two inputs, R and S, and two outputs, Q and Q bar. And I'm not going to put Q bar in there. Q bar is just the opposite of Q. So the behavior, if you remember, if S is a 1 and R is a 0, that's the set operation that forces Q to be a 1. If R is 1 and S is 0, that's the reset operation. It forces Q to be a 0. If S and R are both 0, Q does not change. And the way we can represent that is sometimes we see it like this. Qn plus 1 is just whatever Qn is. So we think of looking at Q at points in time. And whatever value it is right now, that's the value it will be at the next point where we look at it. So it's just a notational convenience. And then we might say something like this. And we'll say if S equals 1 and R equals 1, that's a forbidden input combination. So we may not tell you what happens in that case. So once we have this, we forget about this. Well, we don't forget about it. When we're working with an SR latch, we're thinking of this and we're thinking of this. Okay. All right, so Tuesday we'll put these into a D latch, which will be easier to use. This will be a true memory that lets us say, here's a bit, remember it for me. When we come back and we say, what's that bit I asked you to remember? It will tell us what the bit was. And then we'll start building up from there. And we'll very quickly get into state machines. Definitely by next Thursday, we'll be building complex machines using all of this. And then we're off into some really fun stuff. All right, I will see you next time.